right, because we have the unexpected luxury of 3 speakers today, I'm going to get started right at 8 o'clock. So good morning, everybody, and welcome to the October version of IIDR Rounds. I'm Lori Burrows. I'm the Associate Director of the IIDR. And it is our pleasure today to have 3 speakers, which is unusual. Let me introduce them to you. So our first speaker is Dr. Jeffrey Pernica, who's an associate professor in the Department of Pediatrics and an associate member of both the Department of Health Research Methods, Evidence, and Impact, and the IIDR. He's the co-chair of the Ontario Immunization Advisory Committee and an executive member of the Pediatric Investigator Collaborative Network on Infections in Canada. His research focuses on optimizing the diagnosis and treatment of respiratory diseases, enteric diseases, and sepsis. And today he'll be speaking about novel diagnostics for pediatric respiratory diseases. It's that season. Our second speaker will be Dr. Yingfu Li, who's a professor in the Department of Biochemistry and Biomedical Sciences. He's published extensively on functional nucleic acids, including over 300 research papers, review articles, and book chapters, and received multiple recognitions. He holds a Canada Research Chair. He's received the New Investigator Award from the Canadian Institutes of Health Research, the Premier's Research Excellence Award from the province of Ontario, and the McBride Medal from the Canadian Society of Chemistry. Our third speaker is Dr. Leyla Soleymani, who is a professor in the Department of Engineering Physics and our Associate VPR. She's leading McMaster's entrepreneurship and commercialization portfolio and has extensive experience in developing biomedical technologies for rapid disease diagnostics, health monitoring, and reducing the spread of infectious diseases. She's a university scholar, a Tier 2 Canada Research Chair in miniaturized biomedical devices, and a member of the Royal Society of Canada. Today, Dr. Li and Soleymani will be speaking about diagnosing infectious diseases with aptamer-enabled electrochemical sensors. So thank you for joining us, and I will hand the mic over to Des.
Thank you so much. So today we're going to be talking, as you said, thank you so much, Lori, about diagnostics for pediatric respiratory disease. Oops, that didn't work. So just at the very beginning, I'm going to talk a little bit about antimicrobial stewardship or using antibiotics properly. And I was just saying to Lori that for this particular audience, I don't think I need to spend much time saying things like, you know, AMR is an actual problem. What I will say is that it has been explicitly noted by multiple organizations. So this is a document from the World Health Organization saying explicitly that doctors should prescribe antibiotics based on evidence. You know, this should be normal. And this was echoed in this recently released, you know, Pan-Canadian Action Plan on AMR, which explicitly called for research to help doctors prescribe more appropriately. All this to say that I think, you know, reducing child antibiotic exposure is an end. It is not just a means. So let's talk about various, you know, kinds of disease where novel diagnostics could be useful. And we'll start with streptococcal pharyngitis. I think most of you have heard of strep throat. You get a sore throat, you get a fever, you swollen glands, you feel not great. And in North America, the standard, at least for, you know, children, is to treat with antibiotics, because this not only makes it go away faster, but it will prevent rare but serious complications such as rheumatic fever, right? But for those of you who don't have children or haven't seen a movie, normally what happens to kids when they get strep throat is that, well, they feel sort of sick for a little, and then their throat gets worse, and then they get a fever, and then they get miserable, and then it is decided at some point that enough is enough, and they need to go to the emerge. So you drive to the hospital and you sit in the waiting room for 4 hours because, you know, kid doesn't feel great, but they're not that sick. Like streptococcal pharyngitis doesn't kill anybody. And then you finally get into the doctor and you get swabbed. And then at that point, what is the standard of care is that the family is given a prescription and they say, if we call you because it's positive, then you should fill this script for antibiotics and give the antibiotics. And then what happens at the swab at our institution, just so that you know, okay, is that it goes to the MUMC core lab where it gets received, and it's a box, and it waits for the person in the van to drive it down to the general where it gets received. And then the robot plates it on chromogenic agar, and then we wait for a day to see if there's orange colonies, right? And if there are orange colonies, then a tech picks them off and does an antigen test. And if it's group A strep, then that goes into the lab information system. And then it waits for the doctor to see that. And then the doctor has to call the family. So really, like what this family is doing on Sunday and Monday is this, right? Kid maybe gets a little bit better or not, but they're still not totally better. And so the parents are not happy. And then who knows what happens with the antibiotics? Like maybe they fill the antibiotics anyway, because why would that hurt, right? And then hopefully on Tuesday, they get a phone call, assuming that, it doesn't go straight to voicemail, and there's voicemail available, and yada, yada, yada. So this would appear to be a clinical scenario where novel diagnostics, you think, could do a very good job of this. And it just so happens that there's a number of commercially available platforms that are Health Canada authorized for the detection of Streptococcus pyogenes, so their sensitivity and specificity are comparable to culture, and they take 6 minutes to go, which is an improvement over previous rapid technology that were insufficiently sensitive in children to rule it out, right? And so again, if the performance character, the analytical sensitivity and specificity are okay, then this is a scenario where you sort of know what's going on, right? Because if it's a positive, the kid needs antibiotics. If it's a negative, the kid doesn't need antibiotics. That is essentially it. I mean, there are potentially more cases than this, but in general, this is the story. And so these test results are immediately actionable, and doctors love having this available, because then that saves the whole, I'm giving you a prescription, but don't fill it yet. But why shouldn't we fill it? Because we're not sure what it is, because it might be viral or bacterial. And these parents haven't been sleeping so great because the kid is sick or this and that, and someone doesn't understand, okay? And it's a hassle for everybody. And families, for the same reason, love being told right away, this is viral, this is bacterial, you are done. And so I was writing a grant, and someone's like, why are you even bother? Why are we even testing this? Why don't we just do this? You sort of could make that argument because people would like it a lot better. But there are actually other relevant considerations. And aside, the obvious one is cost. So figure that a positive by this way is maybe, twice as much. A negative by rapid testing is a lot more than a negative is by standard, due to the infrastructure that's already been established for the lab. But it's also, okay, my microbiology colleagues can talk to you about the difficulty in operationalizing a test outside of a lab environment. I think laboratorians often forget that non-laboratorians are idiots when it comes to doing lab tests, and QA/QC is an integral part, and is a necessary part of maintaining a test for clinical use, right? And that is not easy when you are placing a device in a clinical environment. There are also questions about, it's good that people like something fast, right? But will it actually lead to more important outcomes than that? Will it actually lead to more kids getting the appropriate treatment? Will it lead to kids actually getting better faster, right? You think that it will, but will it actually? Will it actually lead to less doctor shopping while they're waiting for the lab result? And will it lead to less group A strep spread among families and close contacts? Because these outcomes, okay, being happy is good, right? But these outcomes are more important than caregiver or clinician satisfaction. And if there are these benefits, how much does it cost per, 10% better treatment, for example? And so this is why we are doing this study. We started it in early 2021. We were supposed to be done by now, thank you, COVID, but hopefully, okay, we should be done by this spring. And I am hoping, we know that people love it, right? The question is, how much benefit will there actually be in terms of other outcomes? So let's shift gears a little bit. Strep throat, everybody knows about that. Something else that people know about is pneumonia, and community-acquired pneumonia in particular. I love talking about pneumonia because when you're talking about child health, pneumonia has a much bigger impact on strep throat. Like strep throat generally goes away, right, if you don't do anything. Pneumonia is the second leading cause of child hospitalization in much of the United States. In Ontario, it is the leading cause of child hospitalization outside of the neonatal period, right? So this is a lot of morbidity. Now, you'd think with something that is so important, we would know what it is, okay? As a self-styled pneumonia expert, I can tell you I don't really know what pneumonia is. So we would generally presume it to be infectious, but there are no consensus criteria. So people will say like, well, you should sort of be sick all over with like fever or, you know, malaise, and you should have like breathing problems, like fast breathing or cough, which makes sense, right? The problem is that there's lots of non-pneumonia things that also do this. Asthma exacerbations, you can have fast breathing and cough. That's not pneumonia. Viral bronchiolitis, you can have fast breathing and fever and cough, and that's not pneumonia either. Some people will say, well, a chest x-ray will solve it. Unfortunately, with child disease, that is not true. So everyone will agree if a kid has a giant pneumonia, everybody will agree if the kid's x-ray is normal, but most pneumonia is somewhere in the middle where you know, pediatric radiologists will argue with each other and with themselves, right? And so this is why you have different recommendations around, you know, chest radiography from professional societies. Now, why am I going into all this detail? Only to tell you, to give you an idea of why this idea of pneumonia is so problematic. It gets much worse from here on in, okay? Because not only do you not know exactly what pneumonia is, but it is caused by a host of different pathogens, right? Most, when you think about burden of disease, most pneumonia occurs in preschoolers. Preschoolers very commonly develop viral pneumonia. This has been known for literally decades, right? The problem is that little kids often get bacterial co-infections, right? And so this was shown in this seminal study that I reference constantly of 2,500 kids that were hospitalized. This isn't like bullshit pneumonia where you go to the family. This is admitted to hospital in the United States over a 3-year period after the introduction of the latest sort of pneumococcal vaccine. And what you can see here is that a huge proportion of these kids had either viral disease or viral bacterial co-infection, right? The trend is exaggerated in the young kids, but even the teenagers, right? Teenagers have more bacterial disease, but they still have a bunch of viral disease too. And if you break it down by pathogen, you see these huge VARs for RSV and other viral diseases. And, you know, so in this cohort of 2,500 kids, they found strep pneumo, which I would say is the most important bacterial pathogen in 4% of the cohort. Right? Now, there's reasons for this. I would say that is not only because, you know, viral disease is so common, but because our diagnostics for respiratory viruses are very sensitive, and our diagnostics for bacterial respiratory pathogens are terrible. But still, okay, it seems very likely that a majority of this disease is going to be viral, and yet the practice is to give everybody antibiotics. So the paradigm here is completely different than the group A strep thing, right? Group A strep, you know, you have an answer, yes, no, you know exactly what to do, antibiotics, no antibiotics, you're done, thank you very much, I'm going home now. Pneumonia is this like vague clinical syndrome that is caused by a host of different pathogens, where a good chunk of pediatric disease is viral, but hey, let's just give antibiotics to everybody because we don't know who actually has bacterial disease and who doesn't, and nobody wants to screw it up, right? And so this is one scenario where you think that molecular diagnostics are going to be less helpful, because even though, again, our diagnostics for respiratory viruses are great, like they're the most sensitive diagnostics that exist, and they are very specific. But if you find a virus in a kid with pneumonia, you don't know that they don't also have bacterial disease. And because there are so many respiratory viruses, okay, and no panel will check for them all, even if you don't find a virus, you don't know that they also don't have viral disease. And so the Hamilton panel tests for all of these things, which I would say is the most important viral pathogens, right? But one of the paraflus is not on the panel. The endemic coronaviruses aren't on the panel. Bocaviruses aren't on the panel. Nobody's perfect. The other thing that I will say, in contrast to this group-based rep where you have a single target, right? To have a point of care multiplex panel increases complexity substantially. And this is why these things are like $150 easy, right? Whereas a group-based strep consumable, it's like $30. I've said this before, I'm going to say it again. There is no really good way to detect bacterial pathogens. NPS detection of strep pneumonia is useless for diagnosis of pneumonia, right? Blood cultures are not great, and there's no real validated blood-based test. Like, people are still trying to figure out a blood-based assay, but not yet. So then people say, well, okay, so maybe we can't detect the pathogens themselves. Can we use something else to help? And the answer is not really. Doctors have long been interested in the white count. For pediatric pneumonia, white counts are essentially useless. I don't even ask anymore. I don't use white counts for a lot. Things that people talk about more is C-reactive protein and procalcitonin. You can see these RSO curves at the top. They're a little bit better. They're not amazing. So if you look in this systematic review, the best possible cutoffs for these things have a sensitivity and specificity of around 70–80%, which is not great, right? That is not helpful for individual level decision making when you have one kid in front of you. And so really, we got a number of different ways that we can go with this, and none of them are amazing. So when you think about what we are doing right now, is we sort of divvied it up into non-severe pneumonia and severe pneumonia. So non-severe pneumonia is pneumonia where the kid comes to the emerge, but they generally are okay and they can go home, right? And so what we are trying to do in the emergency is just figure out who is very likely to have bacterial disease. Like, you can't rule it out, right, as we just discussed, right? But who is most likely to have bacterial disease? Because let's not worry about them. And you got to do this fast. Like, yeah, sure, you sit in the emerge for 4 hours, but when you see a doctor, you have like 10 minutes. Like, that's all you got. Like a lab test that takes an hour doesn't sound like much. But for the care of that patient, it's sort of problematic. So we are focusing on finger poke capillary samples that take a few minutes. And the first question is, do you have a giant pneumonia on X-ray? Because if you have a giant pneumonia on X-ray, you need antibiotics. And then we are doing a rapid C-reactive protein. But wait, I thought you said that a single cutoff is not great, and it isn't. So we have multiple cutoffs. We have a high cutoff where we are leveraging specificity. So if you have some big high cutoff, you get antibiotics. But if you get a low cutoff, you don't get antibiotics. And then you have this big zone in the middle, which is sort of a problem when we ask other questions. How is their oxygen? Are they breathing fast? How old are they? Are they wheezing? And then we get an answer, yes, no antibiotics, in an effort to try and stop this sort of indiscriminate handing out of antibiotics to everybody with pneumonia, even though most people have viral disease. And then once we use the biomarker, I also think that respiratory testing is useful, okay? Because if you can find a respiratory virus in somebody that doesn't look like they have a big problem, then that I think is reassuring. And you say to the family, I found this virus, and they feel better. If we happen to find mycoplasma, that is not common in preschoolers. Figure 5% tops, right? But if you get that, that is actually treatable. If they don't get better on their own in a couple of days, they get antibiotics for that. And then the ones that seem low risk but have a negative NPS, because we can't find a virus, we are a little bit more careful with these. And I just had one of these yesterday, right? Kid looked mostly okay when they came in, but they still had fever, and then they started vomiting. And so we brought them back. And because everything was slightly worse, the kid was slightly worse, the x-ray was slightly worse, the blood work slightly worse, they get antibiotics. So the way that we are doing this is a before and after study at the McMaster Emerge. So far, we have 118 enrolled to date. Unsurprisingly, in the control phase where we just let doctors do what they wanted, every single patient got antibiotics, because that is what doctors do. in the intervention phase where we are now, where we try to implement this care pathway, we can cut that by half, which is like a lot. So I am hopeful that we will get funded for an upcoming multi-center trial to do this at scale. Now, kids who get admitted to hospital are different. They are different because they are, have severe disease, and so the stakes are higher. That's bad. The good part is that they are stuck in the hospital, so that's good. So even though most of these guys have viral disease, we don't have to do things in 6 minutes, which really frees up what you can do with diagnostics, right? And so here we are testing a new biomarker. So these kids will get NPS testing as routine. So everybody gets an NPS, everybody gets a blood culture, right? So we're doing all this sort of standard microbiologic diagnostics, but we are leveraging a new biomarker. And I said, oh, before biomarkers, individual biomarkers are not great. So this one, the thing about this particular assay is that it combines multiple biomarkers, and you think that it gets a little bit better. So one of the things in the assay is CRP, which goes high with bacteria, low with viral and non-infectious. But then they throw in these other things, trail, which goes high with viral and low with bacterial and middle with non-infectious, and an IP10. So right. So the idea here is that you combine these and you have a better idea of what is actually causing the problem, and it spits it out in sort of a semi-quantitative scale where low numbers are likely to be viral, high numbers are likely to be bacterial, and then you have this bit in the middle where it can't tell either. But as you might expect, its performance characteristics are substantially superior to either CRP or procalcitonin. This has been demonstrated in thousands of kids in observational studies, of which this is one. And so we have recently gotten funding to start a feasibility randomized trial later this year with kids who are hospitalized with pneumonia that don't have a giant pneumonia, right? They don't obviously have a bacterial disease, and they don't have a bacterial pathogen in a blood culture. So in this feasibility study, we're going to hopefully enroll 100 kids and randomize them to standard care, which is essentially antibiotics for everybody, or this new test. Those kids with the new test who have a viral score, we will stop their antibiotics and then see how they do by day 4. There is so much viral disease. I am very confident that this should work. Well, I mean, I've been wrong before. We'll see. But we'll see what happens. And then again, the plan would be to do a larger trial afterwards. So my big take homes are really, there is no end of ways in which we can leverage novel diagnostics to improve patient care. Our entire clinical model is predicated on diagnostics. So I mean, like there is always a way to figure out how to do better for patients with new diagnostics. But the effectiveness and the usefulness of a given diagnostic is very context dependent. Even with pneumonia, it depends. Things that would be great for severe pneumonia won't work in non-severe pneumonia. It all depends on what are the practices of care for individuals with that particular kind of disease. And I think I am on time, which has never happened before. Thank you so much.
Thank you, Des. We'll switch over to Yingfu now. And I would remind everybody, if you have questions for our speakers, please put them in the Q&A and we'll answer them at the end.
Great, that's for the wonderful talk, and you ended up so well. Clearly, diagnostics are important. Leyla Soleymani and my lab teamed together for making new diagnostics based on aptamers and electrochemistry. I will introduce the talk by tell you a little bit more about aptamers and what we have done in the last few years. If you look at these slides here on the left, I'm showing you DNA structure, which the DNA double-stranded configuration in cells. And on the right, I'm showing you here is actually the RNA molecules in cells is single-stranded molecules, and many of them actually create functional structures, like here the ribozyme, and also many structures, they fold into antibody-like structures that bind to different kind of molecules like metabolites or even proteins. So the idea that many of us have is that can we actually make single-stranded DNA molecules that just like ribozymes or aptamers in cells that it can bind to target of interest. And now many studies has been done. I'm showing you here is a small DNA molecule is actually doing the ribozyme-like function. On the slide here, I'm showing you 4 small DNA molecules, one bind to protein, thrombin. These one on the top right bind to ATP. The bottom 2 are DNA enzymes. The enzyme made of DNA on the left is just doing the cutting of this RNA unit. Then on the right, that you could actually link the aptamer to the DNA enzyme that create this aptamerzyme that are dependent on the target of interest. The reason that we're interested in this is that we can actually create these things in a test tube through the use of a huge combinatorial library that contain as many as 10 to the power of 15 different DNA or RNA sequences for people studying RNA. And at the end of this kind of a cyclic process that involves selection amplification, you'll get one or few species that can do wonderful things, as demonstrated initially in these 2 seminal papers published by Jack Shostak and Larry Gold many years ago. So my lab then is really working on function nucleic acids or functional DNA sequences, specifically DNA enzymes and DNA aptamers, using in vitro selection technique to derive these molecules. Then we team up with people like Leyla and Das to really explore these molecules for diagnostic applications. So one thing we like to do a lot in the lab is called RNA cleaving DNA enzyme. Basically, the DNA enzymes, they fold up more like the cartoon shown here, right? So bind to a target. So this is the catalytic domain. We'll cut RNA unit. Everything is synthetic, right? But the RNA unit contain a fluorophore to its left and quantity to its right. So it will generate fluorescence upon cleavage. And as I'm showing you here, right? So this is the E. coli responsive DNA in the panel B here. So at this moment, you add E. coli, you'll see the fluorescent generation, right? Then you add other bacteria that will not produce any signal. And it's a simple DNA sequence. You can buy this cheaply from, you can make it in the lab, or you can actually purchase like you do for the PCR primers. So over the years, we have made DNA enzyme for many pathogens, C. difficile, which is the big one, and also H. pylori, Legionella pneumophila, Staph aureus, Salmonella typhimurium, and the latest one we have is Fusobacterium nucleatum. I don't have to tell you that these are important bacterial species, and each one of them actually cause medical problems. And so I give you one example here that we made, a sensor we published in 2021 that a DNA molecule, they are specific to be activated by this bacteria, Legionella pneumophila. And here's basically just data. And then we'll also have these sequences, and we have tested this multiple times for bacterial detection. And so then recently we also made a DNA enzyme-like molecule that target RNAs from Salmonella typhimurium. And that sensor is being used to detect this foodborne pathogen. And so that's on the DNA enzyme. We use DNA enzyme for bacterial detection, and later we'll tell you application of one of the DNA enzyme in her talk, and I will hold on the biosensor side. We'll also make aptamers as viral sensors. Thus indicated that maybe diagnosis of viruses might be a little bit more challenging, or maybe the treatment of the viruses might be minimal challenging. So we can make aptamers either as diagnostic tools or potentially as therapeutics, as we are currently doing with Matthew Miller's group at the IIDR. And on this slide, I'm showing you that two viruses we have been working on. One is SARS-CoV-2. The other is animal virus called pulsi epidemic diarrhea virus, PEDV. And on the sunset part, Leyla will talk a little bit more about what we have been doing. I will focus on how we generate or further optimize the performance of the aptamers targeting these viruses. And so, as you know, SARS-CoV-2 is important that causes COVID-19. Starting in 2020, my lab, in collaboration with many labs at McMaster, selected many these little DNA sequences, artificial sequences that bind to the spike proteins of SARS-CoV-2. Okay, so I show you here, these are 3 synthetic molecules that bind to spike protein at nanomolar binding affinity, right? And so we then team up with Leyla's group. We create a dimeric aptamer, and the dimeric aptamer now has significantly improved the binding affinity, improved by as much as like 50-fold. And then we made an electrochemical sensor that can do the test in 10 minutes. We'll also team up with several clinicians, which I acknowledge later in my talk, that use the patient saliva samples to validate these tests that give us a sensitivity of about 80% and specificity of 100% use, human saliva samples. And the problem working with the virus is that particularly like the surface proteins that are used to attack human cells, they mutate all the time. And because of the use of vaccines or other treatment methods or natural evolution of these viruses. For example, I'm showing you here, this is the SARS-CoV-2, the Y type and Delta and Omicron, and these red spots indicate the mutations, okay? The problem is that when we actually looking for aptamers that bind to the spike proteins, they keep on mutating. So the original aptamers we generated may not be effective against the variants of concerns. So we come up with a solution of isolating universal aptamers. They don't care about mutation, but instead I recognize the regions either they cannot be mutated or they're less prone to mutation. For example, these aptamers we call MSF52. We derived using a unique method that now being patented that give us these aptamers that are really not sensitive to the variations of mutations. And so as you can see here, so we started the original aptamer, we started with Y type, the Wuhan version, all the way to the Omicron, and the binding affinity are very, very similar. So this is a very unique aptamer that we generated. The other thing we often do is to really try to create a high affinity aptamers based on the property of the targets. And for example, the SARS-CoV-2 is trimeric protein. So we are capable of engineering a matching trimeric aptamer that bind to these protein with great affinity. And so the original aptamer has a nanomolar binding affinity. When we actually engineer the aptamer into the trimeric form, the binding affinity actually increased as much as 2 to 3 orders of magnitude. Whereas actually when we test with pseudovirus, which express multiple copies on the particle surface, the affinity increased by as much as 4 to 5 orders of magnitude, which surpass the performance of most antibodies. So we can do this kind of a trick after the creation of the aptamers. Now, I also want to point out that to set up the talk for Leyla. So for the PEDV virus, that's a pulsi infecting virus. We also did a selection for the nucleic capsid protein, which are well-known biomarker for this virus. And we basically did the mutual selection, generate this is the original aptamer, then we make a truncated version of it, and then we test the binding affinity. And at that point, we actually hand over for Leyla to do electrochemical sensing. We had quite a few success with these projects. Now, Leyla and I moving more and more into animal testing as well, in addition to human pathogens. So quickly, I just want to make some conclusions. So I just want to say my group is capable of developing RNA cleaving DNA enzyme for diverse bacterial pathogens. So if PES or other clinicians has a need for a sensing molecule made of DNA, feel free to contact us, and we can work together and generate that. We can also make aptamers for diverse protein targets. To tell you two stories, but we actually have done selection for more protein targets. We're also capable of generating aptamers that can avoid mutation problems. And we are also capable of engineering high affinity aptamers through multimeric multimerization using the trimeric example previously in my previous slides. Okay, these functional nucleic acids have been used or are being used as molecular recognition elements for development of bacterial or viral sensors, which Leyla we're going to tell you next. Briefly, I just want to acknowledge my lab. This picture is taken at a retreat. We had a Blue Mountain. We had a fun with a little bit drinking. The funding agencies listed here, and also many collaborators. Leyla, we're gonna continue on with the talk, and I have collaborated with John Brennan, chemist, and McMaster, and also Bruno Selina, Deb Yamamura, and many people. All the people listed here really contributed to the things that I'm telling you about.
Thank you, everybody. Those were fantastic talks. The floor is open for questions. So if you have a question, please type it in the Q&A. I have a question for you, Leyla, about I guess the regeneration of these chips, right? So, you know, I imagine they're not cheap. So are these like a single use thing, or is this something that you can use more than once?
Yeah, so right now we're developing them as single use. It is possible to repurpose them at different stages. So you can basically remove the probes and add the probes to them, or you can basically, in the aptamer-based probes, you can reconstruct the probes. This model has been mostly suggested by our industry partner that you know, let's make them inexpensive enough that they could be discarded. But I from a sustainability point of view, I think in the future there's an opportunity to reuse these chips.
Okay, that's good news. And a question for Duz. If you were to give Yingfu and Leyla your top 3 pathogens that you would desperately love to have diagnostics for, what would those be? Let them get a pen out first.
in any scenario?
Yes.
So, oh, geez. So
dream big, my friend.
Well, you see, I'm the wrong person to ask. Okay. And the reason that is because I just do kids, and all of the volume is going to be in adult medicine, right? Like, I think E. coli is great. Like, so Ontario pharmacists can prescribe for urinary tract infections. Okay. And I think that's weird because they're not sending urine cultures, and so I don't know how that is operationalized at all. Like, that is one of those things that worries me a little. Like, it's bad enough that doctors prescribe for UTIs without culture, but now pharmacists are doing it too. And so being able to find E. coli in somebody's urine in that kind of scenario would appear to be super useful. But any pathogen, geez, like, if there were a way to diagnose strep pneumo in blood or urine even, that would revolutionize the way that we diagnose and treat pneumonia. Like, that would be totally different. People got very excited about a urinary antigen test for strep pneumo that came out that worked sort of okay in adults. All this stuff came out like a decade ago, and it didn't totally pan out. And so now people aren't using it at all. If you could do that, that would fix all the problems in the world. So that's what I would want for me. Strep pneumo diagnostics. blood-based.
Interesting. Okay, you two, you have your marching papers.
Yeah, got it.
And so Yingfu, one question for you. Aptamers versus enzymes or DNA enzymes, I guess. Which is the more promising technology for the future? If you can bring machine learning in to kind of direct how you develop these things.
I think the DNA enzyme is a bit more complicated. I think there will be like case by case when we actually looking at, for example, when we don't know specific biomarker, I tend to use the DNA enzymes because that's easier, practically easier to isolate the probes. But if I actually know a target of interest, I like SARS-CoV-2, spike protein, or M protein, I would be using aptamers because they give us a better way to engineer probes that can be better than traditional protein-based systems. It just gives us more legs of pushing the thing further and further. The DNA enzyme might be a little bit more challenged to do so because we actually have to get the DNA enzyme to do two things. One, that binds to the target of interest. Two, it has to produce the chemical events to report a signal. So I would love the DNA enzyme to be more useful, but I would go with aptamers when I know there's a specific target.
Very cool. So our audience is obviously under-caffeinated because I don't see any questions coming in. So that will just leave me to thank you all very much for your great talks today. And I will see everybody next month for November's rounds.
Thank you so much.